Cauchy's theorem is part of a big family of theorems that you've bumped into either in advanced calculus or maybe in physics. Green's theorem, Gauss's theorem, divergence theorem, what you know as Stokes's theorem, and they're all tied up with a generalized Stokes theorem. And as far as understanding how Cauchy's theorem fits in with these, and also understanding the specifics of Cauchy's theorem, it's important to understand some of the aspects of algebraic topology, especially simplicial homology. So Alfors talks about homology starting on page 137, also in section 4.3, but I think it's important to try to get the big picture on homology because it all fits back in with this generalized Stokes' theorem that I'll state at the end. So let's just jump in. First of all, this says simplicial homology. That means there's more than one kind of homology. And there's a deep theorem of Steenrod's that talks about how different kinds of homology can all be derived from the same set of axioms. And so when you're studying simplicial homology by Steenrod's theorem, you're also studying singular homology and Floer cohomology and Borel-Moore homology and on and on and on and on. So there are many different ways to get at some of this information. And the question that we're trying to answer is, how many holes are in this space? And that's immediately relevant to the way we think about Cauchy's theorem, because we think about having a singularity, especially in the Cauchy representation theorem. We have a singularity, that's a hole in the space. And homology is a very general way of getting at that idea in a very specific way. So we're going to jump in. I'm going to tell you, first of all, what a simplex is. And simplex is the noun form of simplicial. And what it is technically it's the envelope of a set of points that don't lie in a smaller dimension. So here is a 3-simplex. It's a tetrahedron or something like a tetrahedron. We're talking about topology, so any continuous transformation is allowable, and we need to adjust for that. And so that's the idea of a simplex. And so you can just specify that by specifying its vertices and then some specifications about what goes on further. A simplicial complex is a bunch of simplices that are joined together, but there's a condition, and I'm writing something that violates the condition. So any intersection has to be a simplex, and this is not. So I can make this into a simplicial complex. So let me label this, sorry, not a complex in black. And then if I include another edge here, that now makes it a simplicial complex. So you can go into a lot of technical detail about this, but we're doing the highlights. So there's the idea. A simplex, and therefore a complex, has a boundary, and there's some algebra involved, algebra in the sense of modern algebra. And so sometimes you need to pick out a ring, either the integers or the complex numbers or integers mod 2, and do everything in terms of those, and you get slightly different theories with more or less information by choosing the ring. We're just going to leave that unsaid because we're not going into a massive amount of detail. And so in a more advanced algebraic topology or algebra class, you would learn how to adjust for the change in the ring. So I'm just going to write out what the boundary of this simplex is. So it's the whole inside of the tetrahedron and the faces and the edges and the vertices. And so there's an easy way to find out what the boundary is. The boundary is going to be a sum of simplices. That's where the algebra comes into play. And the easiest way to do this is you drop out one vertex, and if that's an even vertex, you have a plus sign, and an odd vertex, you have a minus sign. And that works in any dimension, and so there it is. So boundary of the simplex ABCD, that 3-simplex, takes 4 points to specify a 3-simplex, is minus BCD. So what I've done there is drop the A, but A is number 1, so you get a minus sign. And then next we'll drop the B, and that'll be a plus sign. And then we'll drop the C, that'll be a minus sign. And then we'll drop the D, and that will be a plus sign. So there it is expressed formally. If you look at this, you've got faces, and each face is described by 3 vertices, and if you look, you'll see that you've hit all 4 faces in looking at this boundary. And the thing is also that they're oriented, and so that the orientations add up quite nicely. Okay. So one important thing about the boundary, I should mention this partial derivative symbol is the standard for boundary, and you'll see that again in the most general Stokes theorem, and I've used that before. It's a very, very useful notation, and it reminds you of it really is related to partial derivatives. That's what Stokes theorem is for. Okay, so one thing to notice is that the boundary squared is 0. Now, what do you mean squaring it? It's not a number. This means the boundary composed with the boundary. So if I start with this simplex and take its boundary and then take the boundary of that, I always get 0. That's just a matter of the combinatorics of the plus signs and the minus signs working their way out. And so that part looks pretty good. And that allows us to do something that's pretty algebraic. So what I'm going to do is C sub I, that's a capital C, are the I chains. Those are made up of formal sums of I simplices. And we have this a bunch of those, so I'm going to put a few in. And the boundary takes I chains to I minus 1 chains, or I plus 4 chains to I plus 3 chains. And so I'm going to show you a little bit of what's gone on there. So, and the first thing we'd be tempted to do is say boundary, 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 but this is going to get confusing because we're using the same symbol for many different things. These are very, very closely related things, and so let me toss in some subscripts. And so the subscript for the domain is going to be the subscript of the map. If you're thinking algebraically, this is a homomorphism. So there we go. Okay, and this gives us 2 things. Because the boundary composed with itself is 0, we have 2 sub pieces, and so the reason I'm saying pieces is it depends on the ring. So pieces, it could be modules, it could be vector spaces. So Z sub I, those are the cycles, and those are the things where, well, that's the easy way to say this is that's the kernel of the boundaries. And B sub I, that's the boundaries in dimension I. So that's the image of the previous map. So boundary sub I plus 1. And then because boundary squared is 0, that means that every boundary is a cycle. And so what we get out of this is that we take H sub I, and that is a quotient of modules or vector spaces or there are abelian groups if you use the integers. The H sub I is all of the I boundaries modded out by all of the Z boundaries. That's a lot of formal algebra. And to put this into action, what this means is we've set up an equivalence relation. Anytime you have this kind of something modulo something else, that's an equivalence relation. And the equivalence relation is, I'm going to use, I think, obvious notation, is that C upper I sub 2 minus C upper I sub 1. Upper I tells you which size it is, which of the modules it's in, and then 2 is the second one, and 1 is the first one, is the new term is homologous to zero if and only if there exists something in the next higher dimension with the boundary. I didn't leave myself enough room to write this here, sorry. Well, this is ugly, but it's true. So this is homologous to zero if you can find something in the next bigger dimension whose boundary is the difference. Oh, that sounds really complicated. It's not. It is. It's not. It is. It's not. It is. So let me draw a picture, and this is going to look a lot like pictures you've seen in Alfors. I'm going to draw a couple of simple closed curves, and this time I'm just going to call them CI1 and CI2. And what you have is this equivalence relation holding because this region I'm coloring in has their difference as the boundary. Cauchy's theorem says integrals over homologous cycles are the same. So that's where this comes into play with Cauchy's theorem, and that's the situation. So these homology things, you can go off into a lot of detail on interesting spaces. I want to give you a couple of examples before we hit Stokes' theorem. The first is the ordinary sphere in 2 space, and you're going to say, wait a second, you just drew this picture. I'm going to call it A, B, C, D. But this time I'm omitting the interior. So it's the 4 faces of the tetrahedron, and then the 6 edges and the 2 vertices. So there's the sphere. One thing that you can see is that any 2 points in a connected space are homologous, and I'm just going to illustrate that with the points are down here in the corner and up here at the top. So those are A and D, and A and D are homologous. I didn't pick the most obvious path, but this is a chain consisting of A, B, and then B, D, and the boundary of that is A minus B, so, or B minus A, excuse me. And so anything that is connected, all the zero things are homologous. It is not the case with more complicated spaces. So if I look at a torus, which is a remarkably important space in complex analysis, what, we're not in the plane? Well, yeah, we're not, because you'll see. And what I can do is draw some cycles on the torus. Now, and I'm being, nice and curvy. I'm not following like the simplex rules. And these 2 cycles that I've drawn are homologous, assuming that I need to give them the orientation. And they're homologous because, well, it's probably easiest to illustrate with my arm. I'm not going to draw on my arm. There's one, there's the other. There's this patch of skin in between, and that patch of skin is, the boundary of that patch of skin is the 2 curves. So I'll try to draw that in a nice way on the torus, but there's a situation. You can be pretty intuitive about this, and so there's the deal. We can go into more detail about the ways to find all of the homology groups of the torus, but this will get us started. So let me remind you finally of one thing, the generalized Stokes theorem. And that says, and I'm going to be purposefully vague about what these terms mean, is that the integral over some region, I'm going to call it M, of d omega is the same as the integral over the boundary of M of omega. So omega is an n form that's what you get when you look at like divergence theorem, Gauss's theorem. You get these dx dys, dx dz, so forth and so on. Those are differential forms. Those require a very extensive theory to really get pinned down on, but there's a lot of intuition behind them as well. And so d is the differential operator. It's the same thing that takes a function f, which is a zero form, to f prime of x dx, which is a one form. And then M is some region, and the boundary of M, as we've just been talking about, is if you can express M somehow in simplicial homology or something homeomorphic to M in simplicial homology, then you can find this. This is a deep theorem that connects a lot of different things. Cauchy's theorem is just part of the fallout. In Cauchy's theorem, we're talking about places where the boundary is empty, so this integral is zero. And then now this is where we're now talking about exact differentials as well, as is mentioned in Alfors. So this is a lot of stuff. Most people don't get it the first time, so it's good to have a free pass as far as a first look. And so and then we'll see when we get to the most general Cauchy theorem, which is theorem 15 in Alfors, by the way, we'll see these ideas come up again.